Okay, so we did a lot of electrophilic aromatic substitution. We've done a lot with synthesis already as well with those electrophilic aromatic substitutions. Now, nucleophilic aromatic substitutions, when the benzene is attacked by a nucleophile. So the benzene has a leaving group and wants to substitute that leaving group. So here, hydroxide is the nucleophile, Br minus is acting as a leaving group. Not going to be your typical SN2 reaction, right? This is not an sp3 hybridized center. This is sp2. It's benzene, so there's no backside attack. So we have to do nucleophilic aromatic substitution. Usually abbreviated SNAR, right? Like the SN from the nucleophilic substitution bimolecular SN2, or nucleophilic substitution unimolecular SN1, right? When it's a benzene ring that we are attacking, we are doing SNAR. Now, the benzene ring must possess a strong electron withdrawing group for these reactions. The ring must be electron poor because that makes it a good electrophile, right? We want it to be a good electrophile so that the nucleophile can attack it. The ring must also possess a good leaving group. A halide is a great leaving group. Those are the ones we're going to see. The leaving group must also be ortho or para to the withdrawing group. That just has to deal with looking at when the complex, the intermediate forms, not the sigma complex, because we're not doing electrophilic aromatic substitution. The Meisenheimer complex, that's fun to say, is what we'll see as our intermediate. And that needs to have an ortho-para relationship for the leaving group to the electron withdrawing group. So meta, not gonna work. No reaction, okay? And it's with the electron withdrawing group in the meta position that it's unable to stabilize the intermediate, which we call the Meisenheimer intermediate. Let's take a look at the para relationship first, okay? So hydroxide comes in and attacks the carbon with the leaving group, the carbon of the electrophile, right? We can't kick out that leaving group. That's not going to happen because of a backside attack. Instead, we pop a lone pair onto the rest of the ring, okay? So it does break aromaticity, and we do have the Meisenheimer complex, but the Meisenheimer complex is resonance stabilized. Here's that good one with the electron withdrawing group helping stabilize that negative charge in the ring, okay? And then what we want to be able to think of is we could even go all the way and show resonance with that nitrogen, right? Just to prove that the Meisenheimer complex with the electron withdrawing group in the ortho or the meta or ortho or the para position has extra resonance, extra stability. Beautiful. And then it will condense on itself, restore aromaticity, and kick out the leaving group. Chlorine leaves. Bye-bye, chlorine. See you soon. Finishing that substitution reaction. All right. The substituted phenol product is technically deprotonated under basic conditions because phenol has a pKa of around 10 and H2O has a pKa of 15.7. So yes, with excess NaOH, we do get the deprotonated oxygen. And so we just have to follow it up with step number 2, which is an acid workup, right? So that's where the acid workup was there. So re-put on that proton on the phenol. All right, so nucleophilic aromatic substitution will not occur if the ring does not have a strong withdrawing group. No reaction, right? But if very high temperatures are used, then the reaction can occur. Notice that all we did was we changed and we made it at 350 degrees Celsius, super high. The reaction works even better and doesn't require high temp if a stronger reagent is used. Hydroxide is not the best base we have. Amide is even better, right? So we can see amide work really, really well here, not at high temperatures, just at normal everyday room temperature. But here's the kicker where we know that a different reaction occurs. The regiochemical outcome actually will change the products. If we had a dye-substituted benzene, notice how we put on an electron donating group. I'm going to put EDG here. We know nucleophilic aromatic substitution does not work. Because we want a withdrawing group, we have a donating group. So we're making benzene more nucleophilic instead of electrophilic. What actually occurs is that we receive two products. We see the para is shown, but we also get meta. And so with the reaction of nucleophilic aromatic substitution, that doesn't make sense. So what actually happens is a reaction called elimination addition. And that's the mechanism that will be going through in just a moment. Using isotopic labeling of a substrate, it's really clear that the substrate is occurring at two different carbons. The substitution is occurring at two different carbons. Isotopic labeling is really, really helpful. So you can visualize and label carbons specifically with isotopes by changing one of the carbons to one of the isotopes, carbon 13, you can actually visualize the reaction a little bit better and radio label it. All right, with a nuclear reactor is great. They do this a lot at UCI because UCI has a small little nuclear reactor lab, which is really fun. I worked there when I was in my graduate school, and we radio labeled all sorts of lovely things. It was a lot of fun. With this reaction, it is hypothesized then that we actually eliminate first. Amide doesn't add itself. It actually eliminates first to form a benzyne intermediate. Whew, triple bonded. Yeah, I know the triple bond looks weird, but it actually is viable. And that's how we can explain then that benzyne intermediate. The nitrogen can either add back to the original position, right? And then ammonia is used to protonate, or it can actually add to the other side, right? With a carbon-carbon double bond or this carbon-carbon triple bond. But with this carbon-carbon relationship, either side can be added to. So it's eliminate first and then add. It's opposite of the nucleophilic aromatic substitution. Nucleophilic aromatic substitution added the nucleophile first, then did the Meisenheimer complex, and then eliminated the leaving group. This eliminates the leaving group first, forms a benzyne intermediate, and then does the addition of the nucleophile. So looking at which mechanism do you want to use? Are the reagents electrophilic or nucleophilic, right? If you're using things like acids, that is electrophilic aromatic substitution of benzene. If your reagents are nucleophilic, hydroxide, amide, then are all three criteria satisfied for nucleophilic aromatic substitution? Don't forget the benzene. What are the three criteria? Let's go back. Benzene must possess a strong electron withdrawing group. All right. It must have a leaving group, and they must be ortho or para to each other. Those are the three criteria. If the answer is yes, that all three are satisfied, then we just do the added on, do the Meisenheimer complex, and kick out the leaving group. Wonderful. If the answer is no, then we need to do the elimination, form the benzyne intermediate, followed with addition of our nucleophile. review of reactions real quick for you, just so that you can see all of the beautiful things that you can have benzene do. And our nucleophilic aromatic substitution and elimination addition, right? With all of our examples. These are great concept maps to be able to keep handy for doing practice problems.